So, that is that. So, now let us address an important qualitative and quantitative feature of etalons. We earlier considered 3 etalons and their transmittance plots for f is equal to 200 and I think f is equal to 1 and even f is equal to 0.2. So, there we noted that the contrast between the maximum and transmittance, which in the idealized case happened to be unity, okay, and the minimum transmittance which was closest to 0, okay, for the highest f value which was 200 in the other case. Okay. That is a few view graphs ahead, right. And we also noted that the width of the transmittance function, okay, was the narrowest for the largest f value. So, the width of the transmittance function essentially decreases with increasing values of f and therefore, increasing values of r, right. Better the reflectances of the end, say reflectors of the cavity, the narrower the width of these lines. Okay. So, how do I quantify the width of these lines and how, in what domain, right. So, let us define a quantity which we call the line width. Line width is essentially defined as the full width at half maximum of the transmittance peaks of the etalon. Okay. So, that is the line width of the, that is the line width we are interested in. Okay. So, define this quantity. Okay. Pick any peak, let us pick one of these peaks, let us say the peak that is centered at, sorry, this is not d, this is delta. Again I must make a correction spontaneously. Yeah. So, d is delta, the round trip phase. Pick the peak that is centered at delta is equal to 0, okay, which is sort of an idealization in some sense, and let us find out, again this d should be a delta, okay. Set the delta is equal to delta LW divided by 2, okay, and at this value of delta is equal to delta LW by 2, the transmittance, that is, let us say we took this peak. So, this was delta is equal to 0, okay, and we have on this scale, on the scale of the transmittance, if this is 0, this is unity and we presume that the scale is linear, then here the transmittance function which took the value 1 here should have taken the value a half here, and this happens at 2 points, sorry, okay. Let us mark this to be 0 and this is these are 2 points about delta which has the value 0 here and delta LW by 2 away from the 0, delta LW by 2 away, the value of the transmittance was reduced to half from the maximum. And this is the way, this is how I am defining delta LW over 2, that is such points around the peak maximum in this case delta is equal to 0, where the transmittance falls to a half. Okay. So, this is these are the full width at half maximum, right. So, that is what we essentially want to deduce. So, now let us assume that the reflectivity of the mirror is pretty close to 1. Okay. Again, this should be a delta here. Let us presume that the reflectivity of the mirror, that is capital R, is very close to 1. Now, what are we saying? We are saying find delta LW by 2 such that the transmittance for delta LW by 2 eventually has the value half, right. Solve for this. Now, we have a nice equation. Okay. So, we sort of made this clever assumption that R is close to unity, because that is basically a resonator, right. We are trying to make a high quality, usually in resonator language, we are trying to make high quality resonators, not low quality or poor resonators, right. So, for which we need as best an R as possible. Okay. So, then we can essentially figure out, after a little bit of math, which I leave as a homework for you to do, okay, that the wavelength corresponding to the delta L by 2 is lambda square divided by pi L multiplying 1 minus R divided by the square root of R. Here we have made use of the fact that R is very close to unity. Okay, we make use of this fact. I am not going to really derive this expression for you, just in the interest of time. You can easily wade through this mathematics, or something, this is something which we will do in the tutorial. So, our colleague here will make note of this, that we will do the math to deduce this expression in our tutorial class, but I encourage you sort of earnestly to try this out yourself. It is a good example of working ourselves through this resonator, and possibly these are the kinds of things that we tend to ask you in exams as well, right. So, and I am sort of not shy of saying that these are little things which give us opportunities to test you on. Now, having made this point about line widths, right, we obviously also want to ask ourselves about about what is this, what's so important about line widths and resonators. Okay. Well, here is the point. Suppose I want a light source whose frequency or wavelength is very well defined. Okay, I am talking about precision. I want a light source whose wavelength is very well defined between lambda plus minus a delta lambda, and I want this to be extremely narrow. Why? Because that gives me a very precise definition of frequencies, right. If we are able to realize very precise frequencies at optical wavelengths, and we are able to implement these in the lab, realize sources whose frequencies can be kept to a very narrow window. Okay. That also helps us to maintain time with very high precision, right. So, for example, what keeps our time when we go into and set our time, especially today on a digital device? This computer that is presenting this PowerPoint shows the same time as my mobile phone without much effort, provided they are connected to the internet, right. Please give me a second. They are very well synchronized. However, two analog wall clocks, if they were to be present in this room, would probably not visibly agree with each other. Maybe they would agree to the minute, but probably not on the seconds hand or some. That's a common observation, especially in a coming from a pre-digital era, which maybe I can say I was in at some point. That's a very interesting thing to note, how to synchronize two clocks. So, we somehow understand that the internet is synchronizing this for us, right. But then the internet is just a network. So, who keeps time primarily? Time is primarily kept by some kind of a standard that maintains time, and that standard is a device or a setup or a system maintained somewhere. Most countries have their own local standards, which all of which are in some sense synchronized by the fact that they accept a common definition for time or the second, which we know today is essentially a frequency standard, which is linked to a hyperfine transition in cesium atoms. So, we say that a second is essentially so many cycles of the of a hyperfine transition in cesium, and that defines a second, right. So, that's the way time is kept, but that is also intimately linked very often to a microwave source, a maser. In the case in this case, at least in the case of India, I know that this is a hydrogen maser, keeps actually your national time locally over here, and so on and so forth. Okay. So, it is essentially a laser, a maser. Maser is a microwave laser. This is again a frequency standard, it maintains a very narrow frequency. So, therefore, building these optical resonators is at the heart of very narrow band light sources, frequency standards, and the science of metrology thereon. Okay. Very famously, Arthur Schawlow, one of the co-inventors of the laser and a pioneer and a Nobel laureate, said always measure only frequencies, in the sense of, if you want to further precision science and metrology, frequencies are the thing to measure. Okay. So, at light sources, when we say light sources, these are frequencies of the order of 10 to the 14 hertz, which is sort of an extremely high frequency, beyond the reach of today's electronic technology for that matter. It is these optical resonators which keep frequencies. Now, however, what I told you, what we have discussed so far in this lecture and discussion is the fact that the modes of a resonator, the modes sustained by an optical resonator, a cavity, a Fabry-Perot interferometer, typically have multiple peaks in the spectrum. There are multiple teeth to this spectrum, and the light that comes about is essentially a coherent superposition of all these frequencies, right. So, if you want to maintain a frequency, a much narrower definition of frequency, you want to somehow filter out one of these modes, okay, and have the resonator emit only that out of it. So, you need some additional effort in engineering such a device, right. So, that is precisely what we are working working ourselves towards when we think about line widths and free spectral ranges and so on and so forth. Okay. So, how do we go from the frequency spectrum on the left here to the single mode spectrum on the right. Okay, this is a question that you could also think about. What device could I use to take a source like this and then pick one of the constituent frequencies and essentially have an output that corresponds to just a single mode of the Fabry-Perot here. So, again that is a little bit of food for your thought. Let us think about that and discuss it in the tutorial. But for now, we want to essentially bring ourselves up to a scenario where if I have two resonators, optical resonators, I want to compare them, okay, to say which of the two resonators is better, right. So, from the perspective of keeping frequencies, let us say this is one thing I want to do. I have resonator A on one hand, resonator B on the other hand, right. Let us say these even cost different amounts of money if you are procuring them, or if you are building them, you need to also choose your components to build either of these resonators, and you want to definitely build a better resonator. You want resonator B to be better than A because you want to build the next best resonator. So, how do I quantify the quality of the resonator? So, we are now in a position to define the quality of a resonator, and let us take a step towards that, right. So, the quality of a resonator is quantified by this parameter which we call the finesse of the resonator, okay, a word that we sometimes even use in common spoken language. So, a better finesse is better quality, that is what we tend to associate this adjective with, right. So, the finesse of a resonator defines its quality. We give the symbol F to it, F or sometimes scripted F. We already have one F in our discussion. So, this is another one coming up. So, watch out. It is the ratio of what? Of the free spectral range, which is essentially the spacing between the two peaks in the transmittance spectrum, to the line width. Line width is the full width at half max of a line, one of the peaks in the spectrum. Okay. So, the finesse is the ratio of the free spectral range to the line width of the resonator. So, now let us get used to some abbreviations. So, free spectral range is always FSR. So, henceforth you will find me using FSR for free spectral range, and line width we will replace that by FWHM. Okay, full width at half max is FWHM. So, finesse is FSR by FWHM. Okay. We computed both these quantities, especially in the wavelength domain. In the wavelength domain, FSR was, free spectral range was lambda square divided by L. Okay. Jog your memory, in terms of angular frequencies, this was 2 pi C by L, C is a constant. In terms of wave numbers, it was just 1 by L. In terms of nu, it was just C by L, right, where L is the round trip optical path length. And FWHM, we just deduced that in the previous view graph, it is lambda square by pi L, okay, multiplying 1 minus r divided by the square root of r. We left this as a homework to do, that this is the line width or the FWHM. Okay. So, now the ratio of these two quantities is what we are now seeking to determine as the finesse. Now, finesse turns out to be therefore a very neat expression. It is pi multiplying the square root of r divided by 1 minus r. Note that r is a ratio of two quantities, the transmitted irradiance divided by the incident irradiance. So, it is dimensionless. So, f is also, the finesse also has no physical dimension, it is a number, okay. It is a measure of the quality of the resonator. Therefore, it is not surprising that this is sometimes also referred to as the quality factor of a resonator. Now, this should ring a bell in some of you, especially if you're students of physics or engineering, you have come across this style of dealing with devices or systems earlier too. So, think about your LC circuit, okay, or the LCR circuit. Okay, that was one of the first resonators I suppose we come across in usual pedagogy, and there we define a quality factor, right. So, likewise we define a quality factor here. Now, I have defined the finesse, which is a measure of quality or quality factor for the resonator, in terms of FSR divided by FWHM. It turns out then to be a ratio of the square root of the reflectance of the two identical reflectors which form the either end of the resonator and 1 minus R. Okay, it turns out to be this ratio, but this does not probably give us all the insight that we need. Much of what you learnt in terms of earlier quality factors of electrical resonators such as LCR, where quality factor was energy stored divided by the energy dissipated and things like that, they really hold for optical resonators too. Okay. So, but that is a matter of detail. I would encourage you to refer to additional sources of information like the textbooks that I shared, or any other reliable source. Make sure it is accurate enough as a scholarly source and further your understanding of the same. But then let us exploit the fact next that the reflectivity of the mirror or the reflectance of the mirror is pretty close to 1. It is nearly unity, okay. Especially if we are in the race to make the next best resonator. You want to have mirrors or reflectors of extremely high quality and reflectivity. So, the square root of R is also nearly 1. Therefore, the finesse F is easily written now as pi divided by 1 minus R. Of course, we have replaced square root of R to be unity here. It of course makes absolutely no sense to do that in the denominator, which would then just blow up the value of F. So, F therefore is pi divided by 1 minus R. What does this tell us? One of the factors, one of the key factors in determining the quality of your resonator is the reflectance of the end reflectors, right. So, higher the quality of your reflector, better is the resonator. This is of course important, but this is not everything, okay. A real resonator is 3-dimensional. Please note that. Let's not lose track of the fact that the resonator that we have been dealing with so far is a 1-dimensional resonator. It is a textbook resonator, a textbook Fabry-Perot, a textbook Etalon, a textbook optical cavity. In real life, it is 3 dimension, and there could be other aspects that go into determining the finesse, which is why we have sort of sneaked in an approximation symbol over here. Indeed, FSR by FWHM is a good measure of the quality of a resonator, but I mean, think about a hypothetical scenario where we build 2 resonators, one of which is more say mechanically stable or optically also stable than the other. Okay, what do we mean by optical stability? I will have a little bit to say about it. The point is that then the finesse not only depends upon the reflectance of the end mirror, it also depends upon other factors, okay, when it is being put to use. Therefore, that all this contributes to the quality or finesse of the resonator. But for the purposes of our current study, let us just take the simple 1-dimensional case and understand that finesse is a measure of quality. It is the quality factor of the resonator, and the resonator's quality factor is intimately tied to the reflectance of the end mirrors. Okay. Finesse now gets a few interpretations. Okay. By defining finesse, this was a definition finesse is FSR by FWHM. By defining the finesse thus, I have essentially said turn the spectrometer into a interferometer into a spectrometric device. How so? If we wanted to essentially fit a certain number of line widths inside the free spectral range, of the resonator, let us talk in terms of wavelength over here. Of course, the vertical scale is transmittance, for since we are in the ideal lossless world, the maximum transmittance is unity. Now, we said earlier that we can sweep the horizontal axis by tuning the wavelength of a source, right. So think about this. So, I can use the resonator in many different ways, but if this is a spectrometer, then what is the job of a spectrometer? The job of a spectrometer is essentially to distinguish two close by wavelengths. Okay. If I think of it in terms of a wavelength resolving device, this essentially can fit in and resolve a certain number of distinct wavelengths between the two free spectral two peaks that are on either side of the free spectral range. Okay. Whereas a poorer resonator would have had a transmittance curve like that. This poorer resonator would be able to resolve fewer wavelengths by itself, right. So, that is what we are trying to make a point out of when we determine the quality factor. Indeed, it is the resolving power of a Fabry-Perot interferometer is much better than a dispersive device like a grating or a prism. So, in the scale of resolving powers, it is prism, better than a prism is a grating, better than a grating spectrometer is a Fabry-Perot interferometer. Okay. So, finesse is the quality factor of the resonator. Finesse is also the resolving power of the resonator.